Every time you use a face filter on your phone, or a streaming service recommends the perfect movie, or you see a self-driving car navigate a street, you're basically seeing the ripple effect of a single moment back in 2012. That was the year one single research paper dropped that completely changed the game by finally teaching computers how to see. So let's get into the incredible story of AlexNet. To really get why this was such a big deal, you first got to understand the challenge they were up against. For decades, something that's totally effortless for us, just looking at a photo and knowing what's in it, was one of the hardest unsolved problems in all of computer science. Take a look at this. You know what it is instantly, right? No thought required. But for a computer, it's a completely different story, and a much, much harder one. Right, so you see a leopard. Your brain is thinking about its spots, its speed, maybe where it lives. A computer just sees a giant grid of numbers. That's it. Just numbers representing the red, green, and blue values for every single pixel. It has zero idea what a leopard even is. And think about it. If you change the lighting or the leopard just turns its head a little bit, that entire grid of numbers changes completely. For years, this is where researchers were totally stuck. They were working with these tiny data sets, maybe tens of thousands of images. That's enough to teach a computer to recognize a handwritten number, sure, but it's nowhere near enough to handle the sheer chaos and messiness of the real world. Progress had pretty much hit a brick wall. And then came the ultimate test, a competition that was designed specifically to try and crack this exact problem once and for all. Think of it as the Olympics of computer vision. This was the ImageNet Large-Scale Visual Recognition Challenge, and the goal was simple, but brutally hard. Build a program that could look at an image and correctly tell you which of 1,000 different categories it belonged to. And we're talking about anything from a tiny mite to a motor scooter. With over 1 million images to learn from, this was a truly monumental task. So 2012 rolls around and something just incredible happens. The winner didn't just inch ahead of the competition, it was a quantum leap. Just look at this chart. The second best model had an error rate of over 26%. Not bad for the time, but the winner, this model called AlexNet, dropped that error rate all the way down to 15.3%. A jump like that in a single year is, it's basically unheard of. This was a massive deal. So, of course, that's the big question, isn't it? How on earth did they do it? What was their secret? Well, it really boiled down to two key things: pure, raw speed, and some seriously clever smarts. Okay, let's talk about the speed first. To have any hope of learning from millions of images, the team needed a model with a massive capacity to learn. Basically, a much bigger brain, and a way to train that brain incredibly fast. They built their model AlexNet with 60 million different knobs to tune, or parameters. That was a huge number back then. And to power it, they didn't use normal computer processors. Nope, they used hardware built for video games, 2 powerful NVIDIA GPUs. But the hardware was only half the equation. The real game changer, the thing that unlocked all that speed, was a surprisingly simple tweak to the artificial neurons themselves. You see, before AlexNet, most neural networks used what are called saturating neurons. Think of it like a light switch that gets stuck in the on position. Once it's on, it can't get any more on, so learning just kind of grinds to a halt. The AlexNet team swapped that out for a new type of neuron called a rectified linear unit, or ReLU. This one didn't saturate. It could just keep on learning, and it made the whole process up to 6 times faster. This one little change made training these giant networks actually practical. In fact, their network was so huge, we're talking 650,000 neurons, that it couldn't even fit on one of their powerful GPUs. Those GPUs only had about 3 gigabytes of memory, which sounds like nothing today, right? So they came up with this brilliant hack. They literally split the network's brain in half, ran one part on each GPU, and just had them talk to each other every now and then. It was this clever bit of engineering that made the whole thing possible. But hey, a big, fast brain isn't enough if it's not actually learning the right things. You have to make sure it's not just, memorizing the answers. And that brings us to the second ingredient in their secret sauce, the smarts they use to fight a huge problem called overfitting. So overfitting is this classic problem in machine learning. It's kind of like a student who just memorizes the answers to a practice test, right? They might ace that practice test, but because they haven't actually learned the subject, they totally fail the real exam. The AlexNet team had to make sure their network learned the idea of a leopard, not just the exact pixel patterns of the leopards in its training photos. And they used two tricks that were honestly revolutionary at the time. First, they figured if they needed more data to learn from, they'd just create it themselves. And second, they would basically sabotage their own network on purpose to make it stronger. It sounds crazy, but it worked. So that first trick was called data augmentation. For every single image they had, they would create a whole bunch of new variations. They'd crop it differently, flip it horizontally, even mess with the color balance a little. By doing this, they blew up the size of their dataset by a factor of more than 2,000. It gave the model so much more to learn from, all without having to find a single new photograph. Now, the second trick, dropout, is just brilliantly counterintuitive. While the network was training, they would just randomly switch off about half of the neurons in a layer. Just poof, gone for that round. What this did was it forced the network to learn multiple redundant ways to find the answer. It could never rely on any one specific neuron, because that neuron might just disappear at any moment. It's kind of like forcing a basketball team to practice with random players missing. It makes the whole team more versatile and way more resilient. Okay, so we've got the speed, we've got the smarts. But what did this powerful new network actually end up learning? Like, what does it see when it looks at an image? This part is so cool. We can actually peek inside the network's brain and see what it learned. And these right here, these are visualizations from the very first layer. You'll notice it's not seeing eyes or wheels or anything complex yet. It's learning the absolute basics, the fundamental building blocks of vision, simple lines, edges, color gradients, and blobs. And this is where those basic building blocks start to come together to form something amazing. You showed a picture of a leopard, and its top guesses aren't random at all. They're jaguar and cheetah. It gets the category right. And look at this tiny mite, which is way off to the side of the image. The network still nails it. It's not just dumbly looking at the center of the photo, it's learned to see the whole scene. Okay, but this, for me, is the most powerful proof of all. The picture on the far left is the one they showed the network. The images on the right are the ones the network said were the most similar. And look, it's not finding other elephants in the exact same pose. It's finding elephants from the side, from the front, in totally different places. It isn't matching pixels, it's matching the concept of an elephant. That's a clear sign of real abstract understanding. Honestly, it's hard to overstate the impact of these results. This wasn't just another team winning another competition. This was a complete and total paradigm shift. So what's the legacy? Well, first, AlexNet proved to the world that these large, deep neural networks were the future, and the techniques it pioneered using gaming GPUs, the ReLU neuron, data augmentation, dropout, these are all now just standard practice. Everybody uses them. This single paper was the spark that lit the fuse on the deep learning revolution, and you can draw a straight line from this 2012 breakthrough to all the amazing AI that's shaping our world today. The authors were really clear in their paper that the depth of their network, how many layers it had, was absolutely crucial to its success. Taking out even one layer made it perform worse. And that was back in 2012, with an 8-layer network. Today, we have networks with hundreds, even thousands of layers. It really makes you wonder, right? Where's the limit? How much deeper can we actually go? And what else will computers eventually learn to see?